All right, number one, on a molecular level, describe dipole-dipole intermolecular forces. Now, what we talk about with dipole-dipole, and again, this topic or this unit dealt with forces between molecules, not between atoms. The forces between atoms are a lot different and a lot stronger than the forces between molecules. So whenever you're determining what type of intermolecular force you have between the molecules, especially if it's nonmetal with nonmetal, you first of all have to draw the Lewis structure. You have to know, is that a polar molecule? Is that a nonpolar molecule? That's what we did in the last unit test, and I know that was a couple weeks ago, but you may need to refresh your memory on that. If you're not 100% sure, make sure you can draw Lewis structures and determine if it's polar or nonpolar. If it's a nonpolar compound, every single time it's going to be dispersion forces. That is the weakest of all the intermolecular forces. If it's a polar compound, now you have two options, whether dipole-dipole or hydrogen bonding. Yes, Stephanie?
Wait, what if you can just figure it out without drawing this stuff?
If you can look at it and determine, okay, that we've got the same type of atoms, like what we'll have on here, that's fine. And we'll get to some of those problems here in a moment. Thank you. Yeah. Louis, this is for you, but it's when convenient. I like that. So when we talk about dipole-dipole intermolecular forces, the difference between the forces that are between molecules in a polar compound versus a nonpolar compound is with a nonpolar compound, there's what's called these momentary dipoles. And I think I'm answering question number 2 here when I'm talking about this. But there's this, if I'm looking at, say, like 2 hydrogen atoms, okay, and they're sharing the 2 electrons in between, the reality is they're sharing those electrons equally. However, if you get closer, if you zoom in even more closely, you're going to notice that those electrons are a little closer to that hydrogen for a moment, and then they're a little closer to the other hydrogen for another moment. So there's this shifting going back and forth, what's called a momentary or temporary dipole moment, which is a partial charge. So there's this shifting back and forth where this hydrogen's partial positive for a moment, then partial negative for a moment, then back to partial positive, and so on and so forth. Well, with dipole-dipole, that charge remains constant, because if I'm looking at 2 different atoms, one of these atoms has a greater attraction for those shared electrons than the other. So there is one atom's partial positive, the other one's partial negative. So there's no flipping back. So when I look at a neighboring molecule, say if my hand is one molecule and my other hand's another molecule, if this thumb has a positive charge, this one has a negative charge, there's a stronger electrostatic attraction here because of positive and negatives. However, if this is positive for a moment and this one's positive, they're getting away from each other. So with the dipole-dipole moments, it's stronger than the dispersion force because that partial charge doesn't change. Where with dispersion, it keeps flipping back and forth. And I know that was pretty detailed there. That's why it's on the video. All right. Number 3, the molar masses of 2 carbon compounds are listed below and with their boiling points. And again, this goes back to what I was talking about. Draw the Lewis structure out. If you look at the ethane, and again, I don't have the Lewis structure drawn out with Microsoft Word here, but this is a nonpolar compound. This is a polar compound. Ooh, I need to quiet that. So since we have a nonpolar compound versus a polar compound, the molar masses are relatively the same. However, the boiling point is almost double. Not quite, but it's much larger. The reason? What type of bonding is going on between the molecules here? It's polar. I'll tell you it's polar. And this one's nonpolar. Hydrogen bonding. Okay. And what you have is a carbon in the middle, then an oxygen, and a hydrogen. So we do have a hydrogen attached to an oxygen. And you can only see that if you draw the Lewis structure.
So explain the large difference in these, because
the hydrogen bonding is much stronger than the weak dispersion forces. And again, if you have strong intermolecular forces, it's kind of like it's a strong bond. If you have a strong bond with somebody, it's hard to get away from them. If it's a weak bond, you don't care about them. All right, so it's easy to get away. Okay. How are you going to know if it's polar or non-polar? Draw the Lewis structure out. Let me just see if I can draw one up here for a second.
Can you do that one that's on the thing?
Yeah, the ethane. Hopefully it'll show up on the video.
What is this?
It's just a hydrocarbon. Nothing really exciting. So there's the ethane, and notice again the carbon's in the middle. You can treat that as a central atom. The external atoms are the same, there's no lone pairs. So that is a nonpolar compound. Since it's a nonpolar compound, if I have more ethanes around it, they're going to be held together with weak dispersion forces. So nonpolar dispersion, okay? And then with the, was it methanol?
Wait, how did you know that was on polar?
Okay.
Because they have the same horses.
Yeah, in other words, we'll treat the middle as the same and everybody else around it. It's symmetrical and everybody on the outside is the same and there's no lone pairs. However, if you look at the methanol, here's what we have. Okay, so I have carbon and oxygen, so they're not the same in the middle. There are lone pairs, so that's a polar compound. And also we have a hydrogen bound to the oxygen, which makes it a hydrogen bond. Now, you're not required to draw this out. Okay, I would give that to you. We haven't done enough in chemistry to do that yet. Okay, does that make sense? Or a little bit more?
So on the test you're going to draw it out?
I'll have it drawn out for you. Yeah, but with the homework, you can Google it and everything and find out. I always make the homework so much harder. All right, number 4. I like this. When a piece of solid lead is dropped into a pool of liquid molten lead, a little redundant there, will the solid lead sink or float? And explain your answer. I hear a float. I hear a sink.
I don't know.
Okay, hold on. We're kind of in the right path here. Now think about it. When something is a solid, is it more dense or less dense than a liquid form? Should be denser. There's one exception, and it's probably the one that we are accustomed to the most, and that is what? Water. Okay, water's the only one that when it becomes solid, it becomes less dense, and I'm very grateful for that, because if water sank, or I'm sorry, when frozen, solid water sank, we probably wouldn't be here. All the life would be frozen. So since it actually floats, that allows for life to remain taking place underneath. So typically, for everything but water, if it's a solid, it's a lot more dense. So denser objects sink in lesser dense objects. That's why if you place a rock in water, okay, a rock will sink because it's a lot more dense. Not because it's heavier, because it's more dense. Think about this. How does a battleship float? It's less dense than the water. Exactly. In other words, they make those things so big and so expansive that they have to actually do calculations to find out what the density of the battleship is. So when they build and design the battleship, it must be less dense totally, and I'm talking about the total volume of the thing, than the water it's going to be residing in. And it is possible. That's how boats float.
I've always wondered that.
Yeah, you just got to make it less dense. All right, number 5. What intermolecular forces are present between the molecules or atoms in the following substances? With neon. Dispersion. All noble gases. Dispersion. That's in your notes. Bromine. It's a nonpolar compound. So what? Dispersion. HI. That's a polar compound.
Dipole.
Very good. Not hydrogen bonding because there's no NOF. No nitrogen, oxygen, or fluorine. What about D? Dispersion. There's no hydrogen in that. With the P, there's only phosphorus, so again, it's dispersion. So it's a nonpolar compound. Again, kind of redundant question here. Number 6, for each of the following liquids, list the type of intermolecular force. Water.
Hydrogen.
Hydrogen. Very good. Bromine. It's right there. Dispersion. Carbon tetrachloride. Very good. Dispersion. If you draw out the Lewis structure, you'll see that you have a carbon in the middle, 4 chlorines, so it's a nonpolar compound. And again, the only way that you're going to know that is to draw the Lewis structure out. Okay. All right, what is a phase? It's not something you're going through. It's a solid, liquid, or gas. Okay? And everything can exist as either a solid, liquid, or gas. It just depends on how much energy is present. So if there's not very much energy present, it might be a solid. If there's a lot of energy present, it might be a gas. So it depends on the substance. Number 8, what's the relationship between boiling point, external pressure, which we can call atmospheric pressure, and the vapor pressure? So let's start with the external pressure at 1 atmosphere. Okay? The boiling point will be whatever it is, and the vapor pressure will be whatever it is. Okay, so we've got our baseline. Let's say that we increase the atmospheric pressure. What happens to the boiling point when the atmospheric pressure goes up? It does what?
It goes up.
Goes up. Very good. So it's directly related. So if the boiling point goes up, what happens to the vapor pressure? In other words, the pressure due to the pressure due to how much liquid changes into a gas.
It goes up.
Goes down. It's opposite. It's inversely proportional. So if you increase the external pressure, you're lowering the boiling point, which also pushes on those molecules, brings them closer together, so not so much liquid is changing into a gas. So if the external pressure goes up, vapor pressure goes down, boiling point goes up. Okay? So let's flip it around. Let's make the atmospheric pressure lower. What happens to the boiling point? Lower. What happens to the vapor pressure?
Higher.
Much higher. Because now if you take away that extra pressure, those molecules are able to move away, and it's a lot easier for them to change from a liquid to a gas. Why does it take longer to boil an egg in water at high altitude? Exactly. Based on the last question. Based on the external pressure. So even though water may boil at a lower temperature and sooner at a higher altitude, the water's not as hot. So it takes longer to cook an egg. So in Death Valley, when you have the higher atmospheric pressure, now it's pushing those intermolecular forces together, so you can put a lot more energy into the water. Okay, it can hold that extra energy and cook the egg faster. So again, the higher the altitude, the lower the atmospheric pressure, which means that it's going to take longer because there isn't as much heat. So just because water's boiling doesn't mean it's hot. And I'll show you that demo next semester. What's that? No, we're staying right here.
I know. Right up. Yeah. Test tube.
All right, number 10. Why does increasing the temperature increase the vapor pressure of a liquid? Why does increasing the temperature increase the vapor pressure? Yeah.
Temperature increases the rate of evaporation, therefore increasing the vapor pressure.
Perfect. So in other words, even though right now this beaker of water does have a vapor pressure, it's very, very small, it is evaporating. However, if I want this to evaporate a lot more quickly, and during the lab I was going around, especially if you had a Bunsen burner, I kept pouring water into your beaker because it kept evaporating out. Well, the rate of evaporation here is not as fast as if I had a Bunsen burner going under it and it was boiling. So if we increase the temperature of this, a lot more of the water is going to be able to evaporate, which is due to which in turn is the vapor pressure. Good. Predict which substance in each of the following pairs would have a greater vapor pressure: motor oil or gasoline. And again, I'm hoping that you have some life experiences here.
This is hard.
Gasoline, good.
Yes.
In other words, which one would you smell first? That's what this is that game. So gasoline, water or rubbing alcohol?
Rubbing alcohol.
Rubbing
Oh,
alcohol.
so it's which one you smell first?
It could be, because again, that way it has a higher vapor pressure because it's evaporating more quickly.
I
didn't think about that.
Yeah. Perfume or vegetable oil?
Perfume.
And vegetable oil is so thick.
Okay, so the only one I got wrong was the water.
Yeah.
Because I thought like water evaporates. It's Craig, someone is blowing up your phone.
I think
No, I got them all.
You think it's what?
my emails. Yeah, nobody's thinking. All right, number 12. Both carbon tetrachloride and mercury are liquids whose vapors are harmful to humans. If carbon tetrachloride is spilled in a room, the danger can be removed by ventilating a room overnight. If mercury is spilled, someone must pick up the liquid droplets with a special chemical vacuum cleaner. Explain why the spill from mercury and carbon tetrachloride are handled differently.
Because of the levels of evaporation.
Go ahead, Mallory.
Well, that's fine. So I pretty much said mercury, just it takes longer to evaporate, and it's has a stronger. Yeah.
Very good, very good. It takes longer to evaporate because it has stronger intermolecular forces. Carbon tetrachloride is a nonpolar compound. We had that earlier on. So it is held together with weak dispersion forces. However, mercury is held together with very strong metallic intermolecular forces, which we spoke of briefly. So to get rid of the mercury, we need to somehow, some way, physically remove that, because the carbon tetrachloride, you spill it, it's a mess. But if I open up the windows, everybody leaves, we come back tomorrow, it's gone. Now it's out in the atmosphere. But mercury, it's going to take a while. That's one reason why they banned mercury thermometers. Back when I first started teaching, we had them. And we actually had a container of mercury about that big. It is weird. It is weird stuff. Because, I mean, it's a liquid, and you can move it around, but it's just so heavy. It's
Do you still have it?
no, we got rid of that.
Oh.
Yeah. So again, it's all about the intermolecular forces there. You ever dumped it down the toilet? No, we did not dump it down the toilet.
What,
I feel
what
bad for the
stuff has
crocodiles
mercury
down
in it?
What's that?
Does it fish?
Yeah, very small traces, but I mean, it's not like you're ingesting mercury directly.
What other stuff does? There's like the
All right, why is the temperature of a substance constant during melting or even boiling? Why does the temperature plateau? Even though in our lab it didn't do a very good job of that, but why does it plateau?
All the energy is absorbed by the molecules that are going to phase change.
Okay, so in other words, if we're looking at water, for example, if water's at 1 degree Celsius, at 1 atmosphere, it has to be a liquid. Very good. And if it's below 0, like -1, then it would be a solid. So the melting point and freezing point tells us what the temperature of that substance is. Now, the thing about our lab is the thermometer wasn't totally covered by the solid the whole time. That's one reason why we got those fluctuations. Sometimes it was taking the temperature of the liquid, sometimes it was getting the temperature of the solid and the liquid, sometimes it was just getting the liquid. So that's one reason. I hope you guys discussed that in your lab.
Nope.
Number 14, in order to kill bacterial spores, the water in an autoclave, it's just a pressure cooker, must reach a temperature of 121 degrees. How is it possible to heat water to this temperature when water boils at 100?
Oh, I think I know.
Yeah.
I said the water will then change from a liquid to a gas after it's reached 100 degrees Celsius.
That's possible, but also, and I don't think we've talked about this a whole lot, but we can, oh yeah, we did. Take that back. When you increase the atmospheric pressure, what happens at a boiling point? Goes up. So an autoclave is essentially a pressure cooker. Some of you know people that can. I don't know anybody that cans. There's a pressure cooker that's kind of a pot with a twist-on lid. If that thing's, no, it's not a crock pot, it's a twist-on, so it doesn't come off when the pressure increases. If you decide to take that lid off while the pressure's being released, it's kind of like whistling a little bit. If you take that off, the whole contents will blow up in your face. Okay? Because the pressure inside is much greater than the pressure outside, and if you pop that release, it's not a good thing. So you always want that to cool down. It's like a restroom? Oh, okay.
Mr. Craig, do you know that much theory?
No, sir. That's why I'm not dead yet. All right, 15. Explain surface tension in terms of cohesion. Why does water seem to have a skin? Again, when we talk about cohesion, we're talking about the strength between molecules. The greater the strength between those molecules, the cohesion, the stronger that quote-unquote surface tension is. Now, I'm not talking about the layer of pudding that's had a chance to sit open exposed. I'm not talking about the skin in that regard. But again, it's all about the intermolecular forces there. So the cohesion, again, pulls the molecules closer and closer together. 16. What distinguishes an amorphous solid from a crystalline solid? Amorphous means what? No pattern, no regular pattern or shape. Where a crystalline solid does have a pattern. That's all I want you to know. I'm not going to get into the details of what the different types of unit cells are. That's later on in AP. All right, 17. What two factors determine the arrangement of ions in an ionic crystal? Size. Size of the atom and the ratio of positive and negative charges. Good. So cations to anions. Size and charge. 18. Decide which type of solid each of the following elements would form. And again, your choices are metallic, covalent network, molecular, or ionic. And again, going down the list, if it has nothing but metal or metals in it, then you have a metallic solid. If it has a metal with a non-metal, what do you have? Metal with a non-metal. What is it?
Molecular.
Ionic. Metal with a non-metal, so it's an
Oh,
ionic
yeah.
compound. If you have at least two different types of non-metals,
That's molecular.
That's molecular. One kind of non-metal. One kind of non-metal.
Covalent network.
Covalent network. Good. So lithium.
So wait, do you look on the periodic table? to
I
figure
would.
these out?
I would. Yeah.
Okay.
Unless you have it memorized. Good. Neither do I. Lithium.
Malate.
Metal. Sulfur. Covalent network. Good. Nitrogen. Covalent network. Sodium chloride. Ionic. Copper. Metallic. Good. All right, 23. What is the difference between an endothermic reaction and endo and exothermic reaction? So endo means absorbing the energy. Exo means releasing it or losing it. Good.
Is that all we need to know about that?
That's it. Until we talk about heat later on. Yeah.
Do you know the stuff in the parentheses tripping out?
Here's some math. Heated bricks or blocks of iron were used long ago to warm beds. Back in the day. 1.5 kilogram block of iron heated to 155 degrees would release how many joules of heat as it's cooled to 22 degrees? And then there's a specific heat for iron. Notice I gave you kilograms. What do we need to do to that? Get it to grams. Okay. So you have to be aware that we want the same units as we have for specific heat. So again, that equation will be given to you. Convert the kilograms to grams. Wow, that font's big. Can you see that one, Quentin? So around, what is that, 89,000? Okay. Or 89,700.
Wait, I forget how to do kilograms to grams with the 10 to the third thing.
The great Mega King one day called me microwaving nasty pizza. You'll definitely need to know that for the final and next semester. Did you pass?
If I wrote out the number, would it still be considered right, or do we have to have it in?
Oh, write out the number. Yeah. All right. 25. Calculate the final temperature for a 836 gram sample of nickel when 4.55 kilojoules is added to the metal. And the initial temperature of the metal was 23 degrees. So 12.3 is our change in temperature. So are we adding or removing energy? Adding energy. So what do you do to that temperature? Add it. Okay. 35.3. Okay. All right, 26. Dysporium, not one of your 52, was discovered in 1886. That's garbage. We don't care. And the freezing point is 1400, and its boiling point is 2600. If its specific heat is 0.1733, what is the mass of the sample? If wow, there's a lot of fun numbers in this one. 6.22 times 10 to the 5 joules of energy were added to the sample. Sample changes from its freezing point to its boiling point. So what are we looking for here? The mass. Yeah, what is the mass? So rearrange the variables before you throw any values in there and solve. So 2.99 times 10 to 3, or 3,000. Louis got that?
Mr. Craig,
Yeah.
do we have to have it in scientific notation?
You don't. In AP we will. You'll learn. You'll be happy then.
Do you prefer it in scientific notation?
I prefer the right answer. So if you're still struggling with scientific notation, don't do it yet.
Okay.
All right, 27. Copper has a specific heat of 0.38452. A 135 gram sample is exposed to 22.2 kilojoules in an insulated container. How many degrees will the temperature change if the copper will change the temperature of the copper? So again, we're looking for delta T. Change the kilojoules to joules. And the delta T is 428 degrees. I think that's all we're doing with that, right? Yeah. Okay. Good, bad? Easy stuff, right? Ah, here's the question. Is this the last one?
Yeah.
All right. It's easy?
Yeah.
Like, why?
I had no idea.
Because when you get it, it makes sense.
Good, okay.
Oh, yeah.
All right, 28. A swimming pool 15 meters by 4.5 meters is filled to a depth of 2 meters with water. There's no deep end. At a temperature of 22.5 degrees. How much energy is required to raise the temperature of the water to a more comfortable, I don't know if that's really comfortable, that's like almost 100 degrees. That's your body temperature there, 37. And recall that 1 centimeter cubed equals 1 milliliter and equals 1 gram. That's pretty important. And that's for water only. So we can find the mass of this by doing what? Taking the meters and multiplying them together so we get a volume of water. So if we do that, yeah, we'll get there. So we'll do that and we'll find out that we have 135 meters cubed. What do you do with that? Convert the meters cubed to either centimeters cubed or milliliters cubed. I don't care which. Okay, so we can get a volume here. Or I'm sorry, mass. So take the 135 meters cubed, multiply it by, again, there's 100 centimeters in a meter, but we got to cube those guys. And then for every gram of water, it's 1 centimeter cubed. So there's your mass of the water. So get your mass. That's why I gave you the volumes. And then from there, plug and chug. So that's how much energy we need.
Did you get that right?
Yeah.
Today I know.
Hold on, Mr. Day.
Yeah. I just wanted to make sure there wasn't more